Good morning, everyone. I'm Ashish Mishra, and I'm going to talk about specification-guided component-based synthesis from Effectful libraries. This is a joint work with Suresh at Purdue. And so the high-level motivation for this work comes from the following fact that writing correct programs is challenging, and that's kind of the premise most of the works in this conference will be based on. And program synthesis may provide a solution because what it does is it removes the burden of writing the whole program from the programmer and allows her to just give some specifications to which could be translated to actual programs. A particularly interesting flavor of program synthesis is this component-based synthesis works, which are interesting because they mimic the actual development process of the programs. And the idea is to kind of intelligently compose these functions together to solve interesting tasks. The question this work we try to answer in this work is, what happens if these components or the library functions have associated side effects with them? So there are multiple possibilities which could be done at this point. The synthesizer can totally ignore the effects altogether. Unfortunately, this may lead to unsoundness, as we'll see in the follow-up slides. Or the other thing which you can do is you basically defunctionalize everything, and every function returns now a value along with a state change, and do an enumeration of this. And again, this is feasible, but such an enumeration will be very costly. So we try to address this particular challenge in this work, and by presenting a tool called Cobalt, which we'll see in the coming up slides. So before I go into the details of Cobalt, let us try to get some background on the component-based synthesis. So a typical component-based synthesis will look like something like this. So there will be some library functions, which, for example, here we have, this example is taken from an earlier work from Isildilik's group, where we have this a function or a list data structure. Say, for example, there are functions like sorting, for reversing, for taking the n elements from the list and sum. A user typically provides a query, which could be a type signature. For example, here there's a query for finding the best case sum of a given list and k, and some set of input output examples, or in some other works, you can also have some other specifications. And what the component-based synthesis will do is basically it will rearrange these library function in a meaningful way so as to find a solution to the query that is a function which has the same type signature as the query has required, and we satisfy the input-output examples. For example, here it very beautifully synthesizes this function. So, however, the story becomes a bit more complicated when you are looking at components which do have effects. So here I have taken a simple library with two functions, add and top, or the list. But these functions, let us assume they are also working over a heap. There is an abstract heap shown here. So add and top both are working over an input heap, and along with generating the output, they also update the heap state, which is shown just by animation here. So here again, you can throw a query to the synthesizer, and when the synthesizer tries to compose these functions, these library functions together in a meaningful way, what happens is, let us assume that the synthesizer tries to make a call to add, and it gets a new heap state. And now while trying to compose the top now, the problem is that the heap states are incompatible. So we needed a blue heap, say, for example, but we are getting a green heap. So such a composition is not allowed, should not be ideally allowed when you are doing a component-based synthesis. So the challenge is that a sound composition must take the changing heap state into the account. And the other important effect of these effectful components is that now you are working in a space where you have both these heap states as well as values which functions are generating in the library. So you have an exponential increase in the space of the program. So before I go further into the overview of the Cobalt, here's a quick kind of survey of the available component-based synthesis tools. And so normally you can characterize the available component-based synthesis works along three main directions. So the first direction is how the work specifies the libraries and the query properties. So the distinctions are, there are works which use standard language types versus there are works which use richer specifications. Another dimension is about effect granularity. So there are works which are totally agnostic about the effects, as showed into previous slides. Then you can have coarse grain effect understanding, where you just look at read and write of effects in the way of effect systems, or you can have more fine grain notion of effects built into a synthesizer. And the third characterization comes from this how the synthesis procedure or the algorithm explores the space of the programs. You could have standard enumeration, versus you could be doing something more smarter, like interacting between such failures and explorations. So based on those characteristics, you can characterize the related work available characterize the related work like following. So this is a very interesting work named Cypet, which worked over libraries of from the Java language. And along those characterizations, it uses Java types, it is effect agnostic, and it uses a very smart notion of pattern reachability as the actual algorithm. More recently, there has been work where people have seen the use of effects to guide the synthesis process. So this is a last year PLDI work which works over Ruby, and it is aware of the effects, but at a very coarse grain level, in the sense that they use the read and write effects of the functions to guide the search process, and use an enumerative search to do the search. And then there is an extension which of the Cypet work towards the Haskell in the Haskell domain, where you are working with Haskell types, and you are not taking effects at all into account, and here it is the search procedure is an extension of pattern reachability, although change accordingly for the polymorphic structures of Haskell libraries. So where does Cobalt fit into this? So Cobalt basically provides is built or OCaml libraries and is cognizant of the effects. And the main characteristics for the Cobalt are that in the specification language, it has a Hoare-style for specifying effectful semantics. It has very fine-grained effect tracking with pre and post heap predicates. And finally, in the search algorithm itself, it uses an efficient search for this large space of programs by integrating the CTCL and the conflict-driven learning approach using the failures as we do the exploration. So till now, I have been talking about these effects in a very abstract way. Let us try to see some examples of these effects, effectful specifications in the while. So here's a mutable queue data structure, and it has a function, let's say push an element into the queue, and the type signature of the function just says that it takes an event, it takes a queue, and it returns a unit type. Now, along with this type signature, it has some requirements or preconditions when push function could be called. And for example, it says that the push can only be called when the queue length is less than some maximum integer value. And this is, so with the PowerPoint, it covers the overall signature, but basically what it says is that the queue length must be less than the max length. And if that is true, then the function guarantees that the queue is updated with x added to the queue, and the length of the queue is incremented by 1. So here's another example where you have a newsletter database with various fields like newsletter, user, and subscription. And a useful function for this database could be subscribe a user to the newsletter, and it has some preconditions that both the newsletter and the users are member of this database, but the user is not already subscribed. And if that is true, then it guarantees that in the post state, both the users and the user is subscribed to the newsletter. So these functions are coming. So this gives an example of how effectful function occur in the while. So let us now take this example further and try to see a query or component with effects. So on the left-hand side, I have given a library or a table data type. So table data type is basically a mutable list of strings. And there are a set of functions which are defined over this library, or this data type. And for each of the functions, I have given the English language specifications. So one of the important property this library is trying to enforce is the uniqueness of elements in the table data type. So for example, the add table, it only adds a string into the table if it's already not present in the table. The fresh str table basically returns a fresh string not present in the table. So notice that each of these specifications are using the state of the heap or state of the the state of the heap in some sense. So given such a library, a very simple query could be to ask the synthesizer to synthesize a function. It takes a table, which takes a string, and it has no constraints on the initial table. It returns a pair type, and it ensures that the updated table has S as the element of the table, and the size of the table is incremented by 1. So this is a very simple query which can come to your mind that I want to insert, increase the length of the table, and I'm giving a string S to insert. So at this point, what could be a possible solution to this particular query? So as it turns out, if you throw this query to a synthesizer, which is one of the solutions, if you throw this query to a synthesizer, one of the solutions could be that there is this add table function which insert S into the table. So you make a call to the add table function, and you then make a call to other functions which returns the actual type. For example, average length table is a function which returns a float, and size table is a function which returns an integer, and then you create a pair. Unfortunately, this effect unaware solution violates the uniqueness property I talked about, because what happens if S is already in the table? So you cannot, so this kind of composition will be incorrect. So if you give this query to Cobalt or in comparison, the Cobalt is going to, first of all, split the control flow for two cases when S is in the table and when S is not in the table. And for the case when S is actually in the table, which is the first, the if block, then the synthesizer has to find a function which allows it to make a call to add table, and to do that, it makes a call to fresh str, because fresh str guarantees that the string it returns is not already present in the table. So let us now try to see various components of Cobalt, which allows it to do something like this. So first of all, there's a specification language which is used to specify both the library which we pass to Cobalt, along with that the query which we write for the Cobalt. Given this specification and the library, there's a backward synthesis module in Cobalt which takes the specification and does a weakest precondition reasoning to synthesize a solution for the given specification. Now, the weakest precondition reasoning in the verification domain has been used since ages. However, this application of weakest precondition based backward reasoning for the synthesis is something which is which to our surprise is new. And the backward synthesis component can right away find a solution for you, and it can return that solution. But very often what happens is it is not able to find a complete solution. Rather, it can make some progress synthesizing a subterm, and then a new query psi prime. And it passes on to the forward synthesis component of the COBOL. Now, the forward synthesis component of the COBOL basically does a strongest post condition based reasoning to find a solution from a given precondition to the post condition. And this is a standard deductive synthesis reasoning in an effectful world. Unfortunately, such an exploration does not scale for the larger libraries. And to tackle that, we also have another submodule, which is the conflict-driven learning component. Together, they can synthesize the remaining portion of the program, E prime, and you can compose this with the original solution and get the solution. Or if it fails, the forward and CDCL fails, then you have some information about the failed paths and you repeat the process for the backward. Notice that this process is bound to terminate, well, because there are only a finite number of components in the libraries. So let us delve into each of the components and look into detail for them. So the specification language by design uses a very rich language of Hoare types. Now, this is the decision to use Hoare types for the specification language was very useful for us, as we'll see later on in the evaluation, because it allows us to use all the verification effort which has been put in by various verification approaches directly into our synthesis. So here's an example of how you will write a specification of an effectful function in R language. So on the left-hand side is again the same example of table, the add table function of the table. On the right-hand side, a bit gobbled add table function, which is basically saying that add table is a function which takes a table and a string, and the precondition of the function, so the first thing in the curly braces is saying that S is not in the old table. And to specify these kind of things, we have these method predicates of qualifiers like membership and the table and the size, which allows you to write these constraints, and which are later on discharged to SMT as uninterpreted functions. The return type is given as the simple types, and the post condition again uses membership and size to ensure the conditions 1 and 2. So let us look at the backward synthesis and how it works. This is a backward synthesis, seems not to be happy with this. Okay, so the backward synthesis basically takes the I'll take the forward synthesis first and then explain the backward synthesis based on that. So the forward synthesis takes the specification, and for a given precondition and the post condition, it tries to first find a function f such that it could be called in the given context. So first, in starting, it tries to find a function f such that the precondition implies given precondition for the specification implies the precondition for the function. If it does find such a function, then it adds it to the synthesized program, and it updates the specification's precondition to the strongest precondition for the function call against a given precondition. And then it repeats the process to find another function g, which basically could be called under this new precondition as we have. And it keeps on finding such functions till it finds a function such that the sequence of functions such as the overall strongest post condition for that sequence implies the given precondition. So this is a typical, this is the forward synthesis, this is how the forward synthesis works. But very often, if you can find such a solution, then you have the solution as a sequence of those function calls and you return that solution. But very often what happens is that after making some calls, for example, you found a function f and then I and j, you don't have any other functions to explore further. So that is, there are no more functions, or there are none of the functions actually satisfies the condition that the strongest post condition till the of the sequence implies the precondition. In that particular scenario, what the synthesis algorithm does is it backtracks and it goes on to find another sequence of calls. Unfortunately, as it happens, the synthesis algorithm can again go back into another sequence calls which are similar to or equivalent to this particular sequence of calls. And the important question is, can we avoid such similar failing explorations? So now I'll see that we'll see how to avoid such failing explorations using the CDCL component of the synthesis tool. So in order to understand the CDCL version, we have to revisit the query in some sense. So here's the same query which we saw earlier, or the table example. And when the synthesizer takes this query and it uses some top-level goals for breaking the query into the two cases when S is in the table and when S is not in the table. So I haven't talked about how the synthesizer breaks the top-level goal into these conditional branches, but this is pretty standard, and the details are in the paper. So let us assume that for the true branch, when S is actually in the table, it has a subquery which is given here, which is just saying that in the precondition we have that S is already present in the table. So let us now see how there was another slide in between which is missing in the PowerPoint. So let me improvise. Bear with me. So we have this particular precondition, this subquery for the true branch of the synthesis procedure. So let us try to understand how the CDCL search works over this query. So we have such a query, which is where here I have abstracted the pre and post condition for this query with P and Q. It first start in a state, let's say F0. So here, each of the function calls are represented by nodes like F0, F1, F2, and F3 in order to abstract out the details from which are not important to understand this. So it first tries to make a call to, let's say, a function like add table. As it turns out, since S is already in the table, this call is not allowed. And since this call is not allowed, we get this do not enter kind of nodes. So let's call them do not enter node. So at this point, the synthesizer backtracks and it tries to find other paths in the search space. Let us assume that it finds three different calls, a sequence of calls represented by F4, F5, and F6. And then it makes a call to another function. Let's say a function called as clear table. Now there are two different possibilities which will occur at F7. The first possibility is that it will find other such nodes, do not enter nodes. That is those functions which it tries to call, but it's not allowed by the strongest post condition check. However, there will be other functions like fresh str, but unfortunately, it finds that the maximum path length. So in the previous slide, which was missing, I had to explain the bounded search. So let us assume that this is a bounded search where you have to give a maximum path length while doing the exploration. So for certain function calls, it found that you have reached this maximum bound while doing the exploration. And that's why you have to truncate this particular path. So effectively, F7 is a node where you cannot make any further progress because either there are do not enter nodes, or there are allowed paths which you can take, but you have already reached the maximum path length, and that's why you have to truncate those paths. So such paths are basically called as k-stuck nodes because they are parameterized with the value of k. And the synthesis algorithm records some information about these k-stuck nodes. For example, for F7, the algorithm records that the strongest post-condition for that node and the precondition of the truncated functions. At this point, the synthesizer backtracks, and without loss of any generality, let us assume it backtracks to node F5. At node F5, it again sees that it is making a call to clear table, but it has no way to know whether F7 and F9 are related in any sense. So what it has to do, it is again has to go and explore F9. And as it turns out, the exploration under F9 is very similar to the exploration under F7. So there are these same do not enter nodes. However, there's a possibility that you truncated some call under F7 because you reached the maximum path length, for example, for SSTR, but here you can make some more progress on that. Now, this can either lead you to a solution, or it can again be struck because you truncate it, or there is no other path. If that happens, then you have a new k-stuck node which you record. And effectively, since under F9 now the overall tree under F9 is stuck, F9 also becomes stuck node. So the main observation here is that F7 and F9 does have a lot of common exploration which never leads to the solution. So the question we ask is, can we avoid exploring F9 while learning from F7? And we do that, the CDCL search does that by recording two things about the failing F7 node. The first one is something called as a stuck predicate, which is the strongest post condition for that predicate. 2 minutes. And the other one is the truncated predicate. Again, the bracket is totally garbled. So it uses this in a meaningful way to find the discriminating predicate, which basically allows you to discriminate between F9 and F7. So basically, it allows you to find whether F9 is equivalent to F7 modulo this property, whether it will lead to a solution. And to do that, it does two main checks. One is where it says that for every path under F9, there is an equivalent non-truncated path under F7. And the other check is that for every progressing truncated path under F9, there exists a smaller path under F5. If these checks succeed, then it can conclude that both F9 and F7 are equivalent modulo the stackness property. And once you have taken the F7 path, you can safely avoid exploring F9 without the loss of completeness. So we have the soundness and the completeness argument, which says that for a given type environment, library, and specification, if cobalt synthesizes the solution, then the solution must be correct. So I'll quickly go in the view of the time, go into the evaluation. So Cobalt is implemented and publicly available, and I encourage you guys to use it. And the important thing to note here is that our Hoare-type specification language allows you to benefit from the increasing availability of verified software. So for example, all our library specification come from earlier verification of us, and none of them is written by us. And we have applied Cobalt to multiple domains, to a big library of 251 functions and 48 files. So there are mainly three different domains, and in view of the time, I'll just talk about the imperative data structure domain. So we saw the example of the query this data structure has. So for example, you can give given a queue of unique integers and integers, synthesize a program that increases the size of the queue. So the paper shows multiple result tables. Here I have taken the imperative data structure results. On the x-axis are different benchmarks. On the y-axis is the time on the logarithm scale. Let us try to zoom in into some of the interesting cases into this. So I9 and I10 are basically conditionally inserting and removing things from the table. And if you zoom in, you will see 4 different bars like this. So the blue bar is the time taken by the Cobalt. The red one is just the forward synthesis with the CDCL. The back is just the backward synthesis. And the green one is just the forward synthesis without the CDCL version. So first thing to note is that both I9 and I10 have this kind of ratio in the bottom, which is the ratio of the number of predicates to the number of size of the AST nodes. So this gives you some idea of the effort of giving the specification to the size of the program you're synthesizing. And it turns out that this ratio remains quite less for most of our cases. For example, for I10, we see that the ratio is 4 to 425. And so there are some things to notice here. So the backward black bar is missing, and that kind of signifies that the backward alone is not able to synthesize the solution for both of these. And total black, the backward alone fails on 34 out of 47 benchmarks. Another thing to note here is that the blue bar is smaller than the red bar. And on an average, the cobalt, that is the blue bar, is 2 times faster than the forward alone approach. The green bar is much bigger than the an order more takes more time than the other ones, and the no CDCL version on average is 6 times slower than the forward CDCL. There are further other interesting cases, and one is where the cobalt is able to find a solution while the other approaches couldn't. There is a single bar. And we found that overall 5 out of 47 benchmarks, cobalt was able to find the solution while others could not. Finally, we have cases where forward alone fails to find the solution, and this happens for 6 out of 47 queries. So these are the overall conclusions for the evaluations. So overall, we found that the cobalt was able to find solutions where others could not, and wherever others could also find the solution, cobalt was at least twice as faster than the others. There is an extension of the evaluation in the paper, which I won't talk about. And so this was cobalt, which is a bi-directional strategy to synthesize programs, which learns from a stack of failing nodes. And the evaluation basically highlights the techniques in general, and there are further future directions to talk about, which I couldn't take it in this talk in the limited amount of time. Thank you.
Very nice work. Could you tell something about the case studies on which Hoare produced surprising outcomes and the case studies where it has failed?
Yeah, so there are some of the cases where we didn't think that the cobalt will find a solution because there was, so yeah, let's go. For some of the benchmarks, one of the interesting cases for us was that some of the places cobalt and the forward alone has a similar kind of results, and we were surprised about that because we thought that cobalt will always be outperforming the forward alone synthesis. But it happens is in some of the cases, the forward alone is able to find a solution quicker than the cobalt. The reason for that was that the cobalt first make a backward choice, and it has to read, that backward choice never leads to the solution. And then it has to trace back, and then it has to come again with a new backward choice and then find the forward solution. So there were cases where cobalt did not perform as we expected. And those cases are places where the first choice the backward synthesis makes does not lead to the solution in the forward synthesis cases. The more interesting cases were these cases like the Q3 cases, where the cobalt and the backward synthesis both were able to find the solution. So what happens in this is the specification, the specification of the libraries is so rich that the backward synthesis alone is able to find the solution. And that solution is right away used by the cobalt. As compared to that, if you give it to the forward synthesis tool, it cannot find the solution in this case because it has to, this query requires you to synthesize sequences of calls more than 3 along different branches, and that's why the forward alone couldn't find the solution. So for all those cases where the query specification was sufficiently rich, we found that the backward synthesis aided extensively to the solution of the COBOL. And this was to our surprise because we didn't expect the backward synthesis to give us the complete solutions like these things. We thought like the backward synthesis is only able to give us the partial solutions. So yeah, so in these cases, it surprises us in a good way. In the cases where it has to backtrack and try another backward thing, it surprises in a bad way. Thank you.
Due to time constraint. So thank you, very nice talk. If I understood correctly, the language specification is for individual functions.
Mm-hmm.
So what if you have specifications involving multiple functions? Like, so for step, you have push and pop reverse operations. With push and pop, you get the original step. How would your system handle this kind of specification?
Yeah, so that's a good question. And so the question is about what if there are multiple functions and there is a specification. So right now, Cobalt only allows specifications on single functions. But one of the possible future directions is to kind of look at these kind of composite functions or invariant or the oral library where the user just provide invariant. So right now we are not looking at these kind of specification, but that's synthesizing using invariants or multiple functions is something in the future. Thank you.
Okay, thank you. Let's see if we can.